All right, so in this video, I'm going to be explaining the Diffie-Hellman key exchange algorithm, which is an algorithm widely used in public key cryptography. But before we actually understand what the Diffie-Hellman key exchange algorithm is doing and how it works and sort of the motivation behind it, we first need to understand what is the whole point of public key cryptography. It is a widely used field to secure basically information over an insecure channel. And I will explain what I mean by insecure channel. So I'm going to jump straight to it. So by convention, we're going to use the names Alice, Bob, and Eve. So basically, we have Alice over here. I'm going to represent her by a circle. So this guy is called Alice, or yeah, gal. And then we have this guy. I'm going to represent also by a circle. This guy's called Bob. And then we have Eve, represented by this. So, let me use capital. Let me not disrespect Eve like that. So, the whole point is that Alice and Bob are linked in some way, and they're linked for the means of communication. They're basically trying to exchange information to each other, right? So, this is basically, how they're linked to communicate, right? But the problem is Eve is in the room and Alice and Bob only want Alice and Bob to know what they're talking about. So, for instance, let me just give an analogy. It's like if your parents are roasting you, or if people are roasting you, or if let's use your parents. Let's say your parents are roasting you, that'd be very mean, and they speak a native language and you don't speak it. They would be using the native language because They don't want you to actually pick up on they're saying, and so that's how they're sort of obfuscating the information. This is sort of the idea of public cryptography is that we need a means of private communication, but we're in a public setting. So the idea is how do we have this conversation um, to make it easy for Alice and Bob to understand, but very hard for Eve to understand. That's sort of the whole idea behind public cryptography. But this sort of mechanism relies on sort of two ideas. The first idea is a one-way function. So one-way functions are pretty advanced. Like myself, obviously, to get into that, that would take like a lot of math and stuff. But the general idea of a one-way function is that basically it's a function in which if you give the function some inputs, it's very easy to get an output. But if you had to, so it's very easy to go this way. So for example, it's very easy to go this way, given that you have a function and you input some outputs. You just have some inputs. So let me make this better actually. Whoops, let me make this better. So what I mean by this is a one-way function is like this. So let's just say you have a function. I'll use f, and then a, b. This just has a bunch of inputs, right? The idea is that it's going to output something, right? So to output it, it's supposed to be very easy to output it. But if you wanted to take the inverse, if you want to take the output and go the other way and retrieve its inputs from the output, it's supposed to be very hard to do. So that's sort of the idea, right? When Alice and Bob are communicating, they want to communicate using a one-way function. They want to basically obfuscate. They want the information they're obfuscating. And if you don't know what that word means, basically means they want the. Let me just use a better word, more understandable word. They want the information that they're trying to make confusing. They want the information that they're trying to basically encrypt. They want that information to be very easy to encrypt, to be made very easy to make confusing. Because obviously you don't want to do so much work just to make something confusing. It would be ideal for the information that Alice and Bob it would be ideal for the information that Alice and Bob are exchanging to be very easy to sort of obfuscate. I'm just going to use the word obfuscate. Um, so again, it's like that analogy, right? With the parents, when your parents are trying to roast you, like it's very easy for them to use their native language. They're not just going to like create a new language and like start shifting letters. No, they're just going to use the native language. Like it's going to be very easy for them to do because they're both native. But for someone like Eve, it would be very hard to do because Eve is not a native speaker. But then the question is, so we're using a one-way function. So in cryptography, we use a one-way function so that it's very hard for Eve to undo. Like it's very easy for Eve to just given its inputs for Eve to like produce an output, but it would be very hard for Eve to actually undo this output. But there's something also called a trapdoor in public cryptography. So what a trapdoor is that it's a piece of secret information that helps. So since we're using this one-way function, right? Um, the question is this one-way function going to be hard for everyone to undo? And the question is, and the question is, no, it shouldn't, right? Because if it's hard for everyone to undo, then it's going to make so communication is going to be very difficult to do between Alice and Bob, and at that point, they can't even have a conversation because it's going to be just very difficult. Um, so the question is, no, it should not. The one-way function should not be hard for everyone to undo. Um, for example, what I'm saying by this is it should only be hard for the person who's trying to steal information to undo. That makes logical sense. It should be very easy for Bob to undo and for Alice to undo since they're communicating. So the communication is like easy. But for Eve, who's trying to intercept that message, it's supposed to be the one way function. And this sounds really general and vague right now, but it's supposed to be very, very difficult for Eve to undo this information. So the question is, how do we make the one-way function easy for Alice and Bob, but hard for Eve? And that's exactly what a trapdoor is. So it's basically like an extra hint it's an extra hint that is effectively that only Alice and Bob know. And with this hint, right, which is basically what this trapdoor is. So this is like a trapdoor. With this hint, then you can easily outdo unravel or sorry, you can easily unravel the one-way function. You can easily undo it, and basically, so it's just the idea that Alice and Bob have a hint that Eve doesn't have, and so with that hint, it's easy now to go both ways. And then since Eve doesn't have that hint, it's going to be hard to undo. So that's sort of the general idea of public key cryptography is that we communicate, but we have to obfuscate the communication by using a one-way function by making it very easy to obfuscate, but very hard for an observer to undo. But because we're obfuscating information, we need to make sure that at least the people who are communicating can also undo it as well. So it's an analogy like both your parents are native speakers. So for if let's say your mom and dad are talking, if your mom says something to your dad, for your dad to undo it, it's going to be very easy because he's coming from that place. So the trapdoor is basically his background. The fact that the dad comes from China, the mom comes from China, that's a trapdoor. That's something that they have that the person who we're assuming that doesn't speak Chinese, who's like the son or something, that the son doesn't because they weren't taught at a young age, right? And so that's sort of the advantage that Alice and Bob have, and then with that they can communicate. And so that's sort of the entire idea behind public key cryptography. It's just very interesting. But yeah, I think that analogy should sort of make it kind of clear on what's going on here. So you need to sort of understand that when we talk about the Diffie key exchange algorithm, because all those parts that we talked about are used in the algorithm. So before again we even get to Diffie exchange algorithm, we need to talk about, because the basis of this algorithm is founded upon what we call the discrete log algorithm, okay, or the discrete log problem. So it's called. the discrete log problem. Okay, so the discrete log problem, what is it? So first I want to talk about sort of let's remove just this discreteness to it and just say, if I gave you a problem and I said a to the x um, is equal to b, how would you solve this? Well, it's very standard to just say that we can use logarithms, and we would say x is logarithm base a of b, right? That's by definition. These are two equivalent statements, just shuffled in different ways, right? So to convert from exponential form to log form, you can do that, right? But the idea is that if I get, for example, let me just make it more clear. If I gave you to the x of 16, it's very easy to solve this. Like you've literally seen this in your algebra 2 class. It's basically saying how many times do I need to multiply 2 to itself to get 16? And the answer is 4. And so now you're under the impression that like finding logarithms is pretty easy. I mean, even if you have 2 to the x is equal to 17, you can literally um, just from a Google search, you can quite literally get that in seconds. So you should be under the impression that taking the logarithm of things that are not even like that don't even produce like integers is still very easy. Like I literally just did that on my calculator. And I'm just going to give you a it's kind of light in this room. Let me turn on the light. Be way better. Okay, that's much better. But you should be under the impression that I think we can agree that taking the logarithm of something isn't so difficult. I mean, the actual mechanism behind it requires calculus, and I'll get into that, but not. I won't rigorously get into that. But I'm just going to give you a warning. The discrete log problem, you can't just you can't just literally go on your browser and say, what is the discrete log of whatever, and you'll understand what that means. But you can't just do that. So already you should sort of already see why there's this huge disparity in difficulty with finding a normal logarithm and finding a discrete logarithm. Um, but yeah, so I first want to understand like to understand like why this the discrete log problem is difficult. I first wanted to talk about like why is finding logarithms easy. Well, it's the idea that we can use the Taylor series on them. Basically, it's just this idea that logarithms are continuous, right? So because they're continuous, because they're differentiable, then calculus can apply on them. You can use calculus on them. And so to find the logarithm, like some computers, or I think most computers use the Taylor series, and it basically helps them like approximate values. And it takes advantage of derivatives, and because we're dealing with a continuous logarithm, then we can use that, and that's been widely accepted way of finding logarithms. So what the discrete logarithm problem does is that it basically induces difficulty on the problem by removing those features, by removing the continuity of logs. That's why it's called a discrete logarithm problem. So the question is, if we want to make this question difficult, and the reason, I guess, the motivation of making it difficult is because, like I said, that's why I talk about public key cryptography. You want a one-way function. You want something, because think about it. The discrete logarithms are basically inverse functions of exponents. Like you think of them as the inverse, because people exponentiate things, right? It's very easy to exponentiate things, but you can think of logarithms as the inverse thing, right? So when I'm talking about like the discrete log problem, I'm talking about it in the context of sort of, and you'll see this in the Diffie, Hellman, and key exchange algorithm, but I'm talking about them in the context of undoing something, right? So basically, this is like us going from the other way, right? So we're in the one-way function, we went this way, and we wanted that to be like easy. But now I'm talking about in the context of going this way, we wanting to making it hard. So the motivation is we're using this sort of as the because in the Diffie Hellman key exchange algorithm, we'll be exponentiating things, and then we want to sort of undo that exponentiation. So we want that to be difficult. So that's why I'm saying a way to make this sort of difficult is because we saw that finding logarithms are easy because we have these features like continuity and differentiability, then one way to sort of make it hard would intuitively, I mean, this isn't a rigorous like argument, but intuitively you would say, okay, let's sort of remove those features. And if you remove these features, then things are going to get much more complicated. We can't just call our handy dandy calculus to get us out of here. And so the way that people actually sort of make this um, much harder is by inducing mod, right? So basically, they're saying, okay, what is ax to the b? And I'm going to make this, and I'm going to say, what's ax to the b mod n? So basically, this basically adds the discreteness to the problem. This is why it's called the discrete log problem, because we're asking, not only are we asking what's a to the x is equal to b, we're not asking what is a to the x equals to b modulo n. Okay, and if you don't know how mod works, I really just recommend you go quickly do a crash course because I can't really get too like just know what mod works, and then you can watch this video because I don't want this video to go over for an hour, but the way that we sort of make remove those continuous features is by now asking, okay, what is a to the x equals b modulo n? What is that modulo n? And so this is why it's called the discrete log problem, is because this mod n, because modulo is a like it's a discrete, it's a finite like field. We're not dealing with something that's continuous, right? Like um, like it's not like a continuous function. So when we add this mod n, we remove features like continuity and differentiability, and therefore now we can't use calculus. And so we said that logarithms were easy to compute because we sort of had calculus. Now, if we remove that, we would expect them to be difficult to compute. And in fact, this is indeed a very difficult problem to do. No typical high schooler is going to know how to do this. And there's no there's no, so spoiler alert, there is no classical, there are algorithms that make it easier, but I think there is no well established classical algorithm that can easily just solve this problem. Um, so I first want to understand, like, so basically, let me just say this in words so you understand what I'm saying by the discrete log problem. It's basically saying how many times do I need to multiply a to itself to leave a remainder of b when divided by n. Like already, that sounds like that sounds like an unstraightforward, right? Problem. Like the regular log problem is just how many times do I need to multiply a by itself to get another number. Now this is saying how many times do I have to multiply a by itself to get a certain remainder when divided by this. So already you can see, like, the disparity of difficulty is also reflected in sort of translating the math question into its actual words and seeing how one is like way less straightforward than the other one. So that's basically what the discrete logarithm problem is. And that's the basis of Diffie Hellman key exchange algorithm, is sort of abusing the fact that this is a difficult problem. And so if we have this difficult problem, then we can sort of make this one-way function, um, and it will be very hard for Eve to intercept messages. But I do want to do an example. So for example, let's say A is 2, C, use mod 7. So basically 2 to the x is congruent to 11 mod 7. So basically we would say x is congruent to logarithm base 2 of 11 modulo 7. So that's how you write a discrete log. And this is basically 5 because 32 mod 7 is 11, because 32 minus oh wait, I'm actually trolling. Yeah, but this is 4. So actually we do this. But you get the idea. Basically, 2 to the 5th is 32, and then mod 7, you remove 28, you get 4. So that's how it sort of looks like. So it's just adding more concreteness to it. But yeah, that's the discrete log problem. So you kind of understand why it's called discreteness, because apparently, like, when calculus is not like usable, like stuff just gets much harder, and isn't so standard. But yeah, um, now we can talk about the Diffie key exchange algorithm. So This again is, I think, was made by George Whitfield. George Whitfield. I think his name is George Diffie Hellman. Um, but that's sort of irrelevant. We want to talk. We're not here to talk about history, but yeah, we're going to talk about the Diffie key exchange algorithm. Okay, so so what the Diffie Hellman key exchange algorithm? What? How do we start? So again, the way this works, the motivation behind this is the discrete log problem. It takes advantage of that. So the first thing that we're going to do is we're going to have a number and we're going to use G. So there is public information. So there's public information, right? We're going to have Alice and Bob. They're basically going to be, so let me just, to get this situation, labeled, because it's not too easy to explain this. Well, it's easy once you understand it, but to explain it might be difficult. So let me just have my stuff. So we got Alice here, and I'm also freestyling the explanation, so I might mess up. Alice, and then we got Bob. Okay. Then they're trying to communicate some sort of message that's obfuscated so that Eve doesn't understand what's going on. So we have Eve. So basically, what's going to happen is we're going to have public information, right? So think about it. I'm going to use this, parent roast analogy, right? What's public information is the actual word, the combination of letters that's being used. There's no, like, your parents are speaking Chinese, but you don't understand Chinese. The actual public information is the combination of letters that are being used. Okay, and so I just want to quickly say, in cryptography, any message or any combination of letters can just be treated as numbers, because all numbers are in computer science. Computer science is just a string of ones and zeros. For example, the ASCII value of capital A is 65, and 65 in binary looks like that, right? So basically, when I'm talking about numbers, I'm implicitly talking about messages, because the way that we actually process a message is through numbers, right? Numbers don't really mean anything. They're just sort of a layer. I mean, letters don't actually mean anything. They're just sort of just a layer. Like, what's actually in a letter is just a bunch of numbers, a bunch of ones and zeros. Okay, so when I talk about numbers, I'm basically talking about messages. So what I'm saying in the idea is, like, the Chinese analogy is, I'm saying that literally they're talking about the information that you literally cannot make not public is the combination of letters that are being used in that conversation. So for example, in Alice and Bob, there's gonna be G, right? And that's just public information. Okay, so basically G is public. So I'm gonna just say this is like public information. Okay, and it's just the number G, right? We'll talk about what G's we should choose, and what ends we should choose. I'm going to talk about that later, but I'm going to say we also choose, but I want to just talk about it general and then also show what choices of numbers we should use. But in fact, we'll just use G, public information. Another thing that's public information is the modulus we're using. So we'll use mod n, and you'll see later why we should actually use a prime n. In the Diffie Hellman key exchange algorithm, formally n is prime. Um, but for now, I just literally want to talk about how it actually works. So what's public is G and mod n. Okay, the modulus, the G and the modulus we're using. Okay, everyone knows that, right? Because if you're having a conversation in a public setting, there is absolutely no way over an integer channel. There's no way to, like, that's why it's called public cryptography. There's no way to privatize everything. So we have to have public information. So now, Alice is going to privately, because you can still think, like, no one is like a freaking, sorry, I'm gonna use inappropriate language. No one is a literal like mind reader, right? So Alice can still privatize her own information in her head. So what Alice is going to do is Alice is going to privatize an information and choose privatize some information and choose a number A, right? Bob is going to privatize some information and choose a number B, okay? And Eve is just sitting here chilling. So what they're going to do is they're going to calculate G to the A mod n, and that is going to be public. So they're going to calculate G to the A mod n. Uh, so G to the B mod n. Whoops. But this is all public information. Okay. Now, they need to communicate a secret message. And so the way that they do this, the information, the secret, the sort of shared secret key between Alice and Bob, the way they actually sort of, do this is they exchange A and B. So basically, Bob will trade his B over here to Alice so that she can see it, and then Alice will trade her A over to Bob over here so that Bob can see it. And with the A and B, what they can do now is they're going to calculate this shared secret key, and it's going to be G to the AB. So this is private information. So this is the shared secret key. So because they exchanged A and B, which is private, then the shared secret key, the way that they sort of make a shared secret key is by doing G to the A, B, and taking the modulus of that. So everything, we're working in mod n. We're working in a finite field. So we're going to take mod n. So everything is just mod n. Everything is just in mod n. So this is how this is going to be shared. So basically, they can communicate G to the AB. It's a shared secret. And if you think about it, there is no obvious way for Eve to. So Eve knows G to the A mod n. I'm not gonna keep on saying mod n because we're gonna assume that everything is mod n. That's called I think it's called like a finite field. Um, but no worries on that. So basically, we're gonna assume everything's mod n. So again, Eve knows G to the A. Eve also knows G to the B, but what she doesn't know is G to the AB, and only Alice and Bob know that because they're basically sharing their information that they privatize. They're sharing A and B, and so now they can combine that information in a unique way and have this thing that they literally communicated over. So you can see that we literally communicated by swapping A and B. We literally communicated because A and B are not public, but sort of by you know, or actually, whoops. You might. So this is actually not a right way to say it because you might be saying, how do we swap A and B without Eve knowing? So it's not the fact that they swap it, but it's the fact that G to the A is public and G to the B is also public. So they don't actually even have to. They don't even have to even swap their A and B. But because G to the A is public for Bob, then he doesn't even have to tell Alice what his A is. He can just take his B. Um, he can just take his B and then just calculate G to the AB mod M. Hey, give me a second. Hold up. Let me make sure I'm not tripping on something. I'm back. Okay, yeah. So I needed. Sorry, I needed to think about something. So yeah, a major correction is that, said that they swap A and B. Um, that's definitely false. This doesn't happen because obviously then the question would be how would you swap like A and B like securely over this insecure channel, and then that would just if they could easily do that, then why would we be doing all this math? But so my bad. That's not actually what happens. What happens is that because G to the A is public, then you can then Bob can compute the shared secret key because he has his own B. So A and B don't even have to be exchanged. Bob can know his own B, Alice can know his own A. We're not going to exchange that. But because G to the A is public, then we can compute this shared secret G to the AB mod n because G to the A is. So for example, Bob knows G to the A. So what he can do is he can just take this G to the A, raise it to the power of B, and then get put this in mod n, and then boom, and then he has the shared secret key, and the shared secret key is going to be less than n because it's in mod n. And so the question might be like, um, so it's very likely that G to the A, in fact it should, that G to the A exceeds n, and so when we mod n, we reduce it to a number that is less than n. Um, so the idea here is that even though G to the A, we don't need the actual G to the A value, like the one that isn't reduced. We don't need the unreduced value of G to the A, because remember we're reducing it by mod n. We don't need that unreduced value because we can still like we can still calculate G to the A B mod n even by reducing G to the A. So for example, what I'm saying is that if you have a number like G to the AB, what you can do is you can first say you can take G to the A and then raise that to the B. And then if you want to find mod n, you could reduce this number mod n and then use that reduced version to the B to find that G to the A B mod n. So that's what I'm saying is you don't need the unreduced version. You can just keep the reduced version. So that reduced version, G to the A and G to the B, is public. And because it's public, then Bob can calculate the shared secret, and Alice can also do it in a similar manner. So it's this idea that they can still have this conversation with public information because they chose they have their own privatized information that actually they only know themselves. And all that matters in essence is that G to the AB is the shared secret. And so the question now emerges is how would Eve undo all this nonsense? And what she would have to do is if she can find the value of A, then, for example, you have to ask yourself this, right? The reason Alice can find G to A B mod n is because she literally knows what A is because she chose it. And same thing for Bob, right? So if Eve can find either A or B, we're literally cooked, and Eve can do the same thing that those two people did to find the shared secret. So then the question turns into the discrete log problem, right? Eve is going to ask herself, okay, so for G to the X, right? What value gives me some remainder, which is basically this G to the A mod n, that's some remainder, mod n, right? If we can find this, then um, we have this number. Then we're cooked. We have A, and then with A, um, we can find G to the AB mod n really easily, and or with B. And so that's sort of this idea. You can see how the trapdoor is the privatized information that Alice chose and Bob chose, and that's how the house sells. And the one-way function is sort of like unraveling the discrete log problem. But that's sort of how the Diffie-Hellman key exchange works, really unformally. So I want to formalize this now. So uh, the idea now is like, okay, so this is really difficult to explain. Give me a second to sort of think about how I want to come up about this. Hold up. Okay, so uh, I really didn't talk about some of the details in Diffie Hellman key exchange algorithm, but the first thing I want to talk about is the modulus we use in Diffie key exchange algorithm is the assumption that n is prime. So this isn't outright easy to explain why, but n is prime. But the first thing I want to talk about sort of is in the Diffie-Hellman key exchange algorithm, you use something called a finite field, and it's represented by like fx. And basically what this means is just a pretentious way of saying that this is not a partial derivative for those who know multivariable calculus. This is not a partial derivative, but I think there's maybe an asterisk. I'm not too sure. I literally learned what finite fields were like a few days ago, but basically I feel like this is just a pretentious way of saying no. This is a pretentious way of saying that the numbers that you only have access to the integers from 0 to x minus 1. That's really what it is. So it's basically saying mod. You only have access to the integers from 0 to x minus 1. It's a finite field. And so in the Diffie-Hellman key exchange algorithm, you need to work in a finite field. Because, for example, if there, and the reason why this is true is because if there is a solution, for example, so now I'm going to use mod p. If there indeed is a solution to this um, problem, like where's g to the x and some remainder mod p, if there indeed is a solution, there's going to be infinitely many solutions for x. And that, for example, that's going to be very ambiguous. Um, so, like, what I'm saying is that, so, you know how, so let me say this, right? You know how Alice, she finds the shared secret by saying, okay, I'm going to take my g to the a, um, right? G to the a, or I'm going to take g to the b, and then I can just raise it to the a, and then take this mod n, right? Like, this needs to be so that there this needs to be reduced in mod n, right? Because if there's I'm gonna have to pause and think about a way to say this because I'm low-key struggling to explain this. Hold on. Yeah, I guess ignore what I was talking about with the finite fields. I was sort of but we do use a finite field. And sort of ignore what I was talking about for the ambiguity. But I'm first going to talk about sort of what type of GMP we would use for the Diffie-Hellman key exchange algorithm. So first, I'm going to talk about sort of what type of G we would want to use. Um, so this is say what type, like how what type, like how like, so let's say we're working in mod p, right? What type of g would we want to use? So for example, the way you sort of motivate this is by thinking about the brute force algorithm, right? So how would we solve but the brute force algorithm of the discrete log problem? So if I had some g to the r, whoops, so if I had some g to the r and I want to find this, or sorry, g to the x, and I want to find this modulo p, remainder modulo p, then a way to sort of, since we're working in a finite field, so basically I'm basically restricting the fact that we're only going to be operating on numbers from 0 to p minus 1. So for example, when Alice and Bob choose numbers, they're only choosing numbers between well, obviously we're not going to choose 0, but they're choosing numbers from basically between 1 and p minus 1. And so obviously, right, there's a upper bound on x, and so the brute force algorithm sort of shows you what type of g you would want. So basically what you would do is you would say, does g to the 1 work? No, it doesn't. Does g to the 2 work? No, it doesn't. Does g to the 3 work? No, it doesn't. And our hope, because we want this problem to be difficult, we would want this to be computationally expensive. And what I mean by this is we would want a computer to take a while to do this. And so the idea is that, in modular arithmetic, there are these things called cycles, right? And it's basically just like this idea that at some point you're going to reach, so if you start from g to the 0, it's going to be 1. And at some point you're going to reach, like later, like for some g to the m, it's going to be 1, and then the cycle is going to start all over again. In fact, g to the m is called the order of the mod, and I'm not going to really get into that, but basically there are these cycles, right? And so if we're using a finite field, so the intuition is that if there are like cycles, right? If we know like the cycle is like every m, then the idea is that if we know the remainders are, So maybe it's like in the cycle from like zero to m, the cycle is like m long. So technically, a group would be from zero to g to the m minus one. That would be like one group, right? And then you would have that basically copied and pasted from g to the m to whatever next m numbers. Basically, the idea is that you would want M to be very big because if you want M to be very big in the finite field, right? And we're using a finite field P, right? So that means we only have access to the numbers from zero to P minus one. You would want M to be very big in that field, and the reason why is because if M is small, then like the idea is that like if this leaves a remainder of R in mod P, then maybe let's say it's just G squared, then we know that we can eliminate basically what we're saying is that we don't have to try these types of numbers. We don't have to try exponents in the form of, since this is in mod m, right? We don't have to try multiples of m. We don't have to try 1 mod m. We don't have to try 3 mod m. We don't have to try 4 mod m, etc., or all the way up to m minus 1 mod m. We don't have to try those for the exponent. So what it basically does is that it truncates significantly what we would have to try, because we know that in our finite field, because it's going to be very small, then the idea is that it basically just reduces the amount of like useful numbers. For example, yes, we only have access to the numbers from 0 to p minus 1, but if we have a very small finite field, then it doesn't even matter because the only numbers we would actually care about, for example, if we have a g, the like let's say g squared was this remainder, it let g squared left a remainder of r mod p. The only numbers we would care about are numbers that are congruent to 2 mod m, and so we would basically all the numbers that are not 2 mod m in the finite field basically just be useless, and that would just undermine and waste a lot of space in our finite field. So intuitively, we would want m to basically, and this is basically called order. It's basically the smallest integer m, such that g to the m is congruent to 1 mod p. We would want m to be really big, and so the way that we do this is that basically, if p is prime, then there's guaranteed to be a G, and it's called a primitive root. You can search it up. Basically, what a primitive root is that if we're using mod P, a primitive root, we would want G to be a primitive root. And what that is that we're saying that G to the 0, G to the 1, G squared, all the way to G to the P minus 2. And by Fermat's little theorem, it's going to be 1 when it's there. I don't want to get too in depth because then this video is going to be like too long, or it already is. But then the idea is that all these values modulo p are different. Basically, because the primitive root is basically a number that has an order of p minus 1 in mod p. So p minus 1 is the smallest positive integer such that it's equal to 1 mod p. And the reason for this is because if the cycle is basically just as long as the amount of numbers in the finite field, because the amount of numbers in the finite field p is going to be p from 0 to p minus 1. And so we want to make m really big because we just talked about why we should. If the finite field is really big, then basically what we can do is that if finite field is really big, then we literally have to go through each value. Like we don't truncate and we don't waste numbers. We're not wasting any numbers. And so if we, have a very big find order for G, um, then it's gonna be good because then we have to try all those values in the finite field. So now you have to literally try G to the 0, G to the 1, G squared, and so that's sort of the motivation of why we're choosing P to be prime is sort of there is guaranteed to be a primitive element G. And another reason why, so basically, um, the type of G you should use is probably is a primitive root of P. That would give it more security, as I argued before. So another reason is why would we use also a prime mod? Not only does it allow us to guarantee that there is a primitive root, but another thing is sort of saying so basically there is something called Euler's twistant function. It's phi, and it's basically the amount of numbers less than n that are co-prime, that are co-prime with one and n. So, for example, phi of 12, phi of 12 is the amount of numbers. Um, what? Oh, 1, 5, 7, 11. So these are all the numbers that are relatively prime of 12. So phi of 12 would be 4. But basically, Euler's solution function says that a to the phi of n is congruent to 1 mod n. And I'm not going to prove this. I actually don't know the proof of this myself. But what's important in this context is that basically the phi of prime numbers is p minus 1. And you can think of this as saying if, like, the idea is that, like, because, everything starts off as 1 mod n, like, when you're exponentiating things, when you start from 0 to 1 mod n. So that means, like when you're gonna reach one, for example, for example, hold on a second. So if we started from g to the 0, then basically we would reach 1 again when we get to phi of n. And because we want to make phi of n, like, sort of as big as possible, like I said before, like, we want to make that m as big as possible, then we could use a prime number and it would make it as big as possible. So that's why you'd want to also use a prime number. But honestly, that's just some really informal yap on the deeper things going on in Diffie Hellman key exchange. The stuff I explained earlier of how it works is probably all you should really know. This is just a bunch of yap um, about it, but I'll probably formalize it later and put a paper to it. Yeah, but yeah, that's it.